Okie dokes. All right, so I'm going to be talking a little bit about learning skills. So no longer programming robots, but the next generation of robotics. And I believe to be maybe one of the missing pieces to automate further. So that we're all on the same page, I want to start from the very beginning. And what do I mean when I say like learning robot skills or next-gen robotics or data-driven robotics? I mean the same thing. And this is all about moving away from what we've previously been doing, which is where you maybe take in some sort of observation. You would then do some scene modeling, so like object detection and then pose estimation. Like, what is the thing I'm interested in? Where is it in the world? And then moving on to like planning. So, okay, well, how am I actually going to grasp that thing? And then how am I going to get to that thing to be able to grasp it? And then finally, I'm going to control. And my view for quite some time now has been about that this whole kind of part is very, very hard to model for every single problem, especially when dealing with like highly deformable objects, complex dynamics, etc. And so instead, the kind of promise of end-to-end robotics or data-driven robotics is instead to pass in this observation into some sort of black box, which is usually a neural network, and then output some control directly. Okay? So it's moving from these kind of more complicated systems to these simpler end-to-end methods. So want to see some hands up here about if you've seen videos like these recently. So there's normally you'd have some just images coming in and then actions coming out, and people being able to like swap objects and lighting conditions. Has anyone seen these sorts of videos online? Yeah. So you normally see them from like maybe people like Generalists, Pi, DeepMind, etc. So I want to ask the question: this particular video, how long ago do you think this was made? In the order of months or years? Maybe when people want to put a hand up or shout out.
6 months.
6 months ago.
3 years.
3 years ago.
5.
5, 10.
You still look the same age and not that long ago.
Don't forget I have a baby face. This was 2017, almost 10 years ago. So thank you very much, first of all. Yeah, 10 years ago. And my point on this slide is that despite the buzz, and despite now it's absolutely everywhere, this has been going on for quite some time. Okay, we've been doing this for a while. The only thing that's changed is that now you put language in as well, but everything else is pretty much the same. So there's 3 main takeaways I want everyone to walk away from today. The first takeaway is that skill learning is not new, right? Data-driven robotics is not new, and I think it's deployable today. In not every single circumstance, of course, but it can solve a lot of problems. I'd also like everyone to understand a bit about the history of the field, and then how you actually can get started with learning skills today. And so I'll briefly kind of touch upon some of these points through this talk. And so this goes back in 2016. This is using imitation learning. So we're kind of like showing the robot what to do through many, many demonstrations. And this was a paper by Google and showed, I think, 800,000 grasps, which ironically used to sound like a lot, but these days, not so much. But what this really, really showed is that this wasn't really a scalable operation, because we would do all of this data and all this data collection, and then it was just picking from the bin after all. So how can we then get to like home robotics in the future, or like automation across all these different tasks? And so there was a huge interest in sim to real in the kind of like 2016-17 era. And so one kind of way to solve what we call the simulation to reality gap, which is this concept of if I train in simulation, how can I expect it then to operate in the real world, right? Because there's a discrepancy, right? Physics and graphics in sim does not look like physics and graphics in the real world. So this was some work we did back in 2017, where we instead used something called domain randomization, right? So we're just saying, okay, we're not going to try and model the real world. We're just going to put it in all these crazy worlds. And then when it actually gets transferred to the real world's just another crazy world that it's seen, right? It doesn't distinguish between crazy world and real world. And as it turned out, then we're going back to this work that I showed, this works incredibly well. And you get really good robustness to light, and then, of course, the ability to kind of like change the scene, and the robot can instantly react to that. So again, these are all running data-driven methods. Images are coming in, and then it's directly outputting joint positions. And then later on, when I was at Google, we then extended this work further by slightly modifying the idea. So instead of kind of having crazy worlds and then directly outputting actions, and then, of course, during deploy time, having these real-world images coming and then actions come out, we wanted to change it. We wanted to instead say, what we're going to do is we're going to turn those crazy world images, simulation images into like what we call the canonical image. So we're converting it into this kind of canonical simplified world. And then the idea is that we train a neural network to then take in this simplified view and then output these actions. And then, of course, the idea is then that when you give it the real world, it can do the same. And the main motivation for this is that now this guy is only trained in this kind of canonical world rather than all these kind of crazy worlds, and you can get better sample efficiency, right? You need less compute because otherwise you're trying to learn in all these like randomized worlds, and that takes a lot more compute that's actually necessary. And then this is how it looks in practice. You have on the left here the images passing into the Arcan, this adapter, and then the canonical coming out. And then this gets passed then into a neural network. And the real crazy thing about this was this kind of simplified table here. So if you just only used real-world data and that's it, and you spent 580,000 grasps, you'd get 87% in the real world. But if you use this kind of method and you end up using zero real-world data, you'd get 70%. Okay, well, still not as good as the real world, right? But the amazing thing is, okay, well, if I just fine-tune with a small amount of real-world data, I can actually get up to 91, 94, which is better than if I trained on 580,000 real-world grasps. So this was kind of real proof that SIM does have a future to kind of reducing the sample efficiency for these algorithms. And of course, then we extended this work to all sorts of different setups, including driving, off-road driving, and some cloth manipulation, which ironically has now become very popular again. But this was back in 2018. And of course, you've probably seen a lot of these. Domain randomization now is everywhere. And pretty much any sort of like quadruped or humanoid you see is now going to be using this technology. Very briefly on this, benchmarking. In academia, it's very, very important to know if one method is better than another. And back in 2019-ish, we didn't really have a good way of saying, okay, how is one robot learning policy better than another? And so we went ahead and designed this benchmark called RLBench, which put forward a set of 100 tasks across all sorts of different use cases. And then, this ended up being used in quite a lot of papers then over the years. And then more recently, a few years ago, 5 years after, we then introduced BiGym. This was kind of just as the humanoid craze was maybe starting to ramp up, and a very similar concept, putting forward a benchmark for practitioners to be able to assess if one method is better than another. So a little bit about novel architectures. So here, this was back in 2019. What we really wanted to do is push really, really hard on, okay, we know simulation works, we know sim-to-real works, but simulation has its problems, right? It takes a long time to build up the simulator. You kind of have to have a lot of like domain knowledge about like, okay, what's my environment going to look like at test time? And you have to build that in sim. So it's like, okay, this is when I really started to turn back in kind of 2019-20 into like, no, I think we need to focus on trying to deploy in the real world and trying to get better and better, more sample efficient algorithms. And so this was one of the first kind of methods I put forward here, which was the ability to pass in RGB and point cloud or depth information. And then you'd basically have an RL agent, a reinforcement learning agent, to predict, okay, where next in the world is most interesting for me to go. And then you would basically pass that to a path planner. And then you would apply some reinforcement learning. And I'll just focus on the results here. So usually this x-axis, so this is performance, right? So 100%. And then this is number of steps. You can kind of just think of it as time. Usually this would be in the order of like hundreds of thousands, if not millions. And we managed to reduce it to the order of thousands. And then these kind of flat lines here are all kind of like other methods. And then blue is the one I just talked about. And then red is like a slightly earlier version of the one in blue. And this is how it looks. So this is me giving a demonstration. So very similar to the sort of like setup you see in the other room here. So we give 3 demonstrations of turning on a light. It's kind of hard to see, but there's it closes the gripper and pushes down, and then the light turns on. Then it instantly, and this is a live timer, it instantly takes those demos and then starts having a go. So there's actually training in the loop straight away from the get-go, and it's going to keep then trying to be like, okay, what was the human actually trying to get me to do? And I'm going to look at that data while I continue to explore. So it's actively learning from mistakes. And after 30 minutes, it's then able to get its first kind of success by itself. And I'm at the computer by the way, clicking just yes or no. So at the end of every attempt, I say, did you get it or not? And that's it. That's the only feedback it's getting from me. And the only input is an RGBD input coming from this little camera here. And then we later extended this to other use cases. This is opening an oven. The big difference here is that I mentioned it was using path planning. In this case, it was now using learned path planning instead. So that means that you could do kind of skills like this, where previously you'd have to like know, okay, I'm going to be opening the oven, so I have to kind of like go on a very particular trajectory. Now that's actually just learned through demonstration data instead. And then finally, a lot of the stuff that I just showed was kind of assuming that we had a robot arm, right? It was the one assumption we made. And that's how we were able to do like the next best pose, right? Where in the world are we going to next? But then we actually made that even more general and designed a algorithm that could even be used to, say, play Atari games or something as well, right? So it was a more general algorithm, and then we applied it back to the robots. We kind of went full circle. And here's just another example of that system then running. So it's a similar concept where we show some demos. I think in this case it was 50 demos, and then it just starts instantly going. And then you can see this live counter here, and it just gradually gets better and better and better at doing the task. Yeah, so these reds are like failures. So again, it's a human sitting at the machine just saying yes or no. Yeah. Okay. So this is interesting. So back, obviously, big data is like a big thing today, like VLMs, et cetera, and VLAs in particular. But again, we've been looking at this stuff for quite some time. So the idea of, say, taking in some images from the wild, right, videos, how can we actually take these videos and actually utilize them to learn policies, essentially? How can we learn representations and then kind of fine-tune them to actually learn actions? So we looked at taking in a bunch of wild images, 4.5 million in this case, doing some representation learning based on them. And then we would basically take this kind of encoder that was learned, right? So it was learning about the world, and then fine-tuning it then on a particular set of tasks. For example, picking up things, opening a fridge, flipping things, etc. And again, similar concept here. You would then collect a demonstration of doing a task, and then you would then execute this out, roll this out in the real world. And then, of course, as I said, this kind of then later kind of grew and grew this concept of using large-scale data from the internet. And now, of course, we're using billions of videos, et cetera, these days. Yeah, and then very briefly, a bit more recent, everything I've talked about so far is taking in images from the real world, and then you output joint commands or like end effector poses. But we were very interesting to ask the question, okay, well, what's actually going on here? So it's got to learn what the human wants to do, okay? But then it's also asking us to learn this mapping, right? Transforming from image space and then turning that information into joint commands. So what if we instead look at what the vision community has done? They had massive progress over the last 15 years. It's like, how can we ride that even more than what robotics has already been doing? Let's turn robotics just into an image problem. Just literally just turn it into an image prediction problem. And so what we instead did is we got the agent to just draw actions instead onto the image. So it's no longer predicting configurations. It's predicting some representation that it then renders into the image. And then we're going to shove that into then something to decide, okay, what should the robot actually do from that? So it's like a high-level planner, you can think of it. And this is what this looks like in practice then. So these spheres are representing kind of key joints for the robots to reach. And then that's doing the kind of more complex reasoning about, okay, what does the human want me to do? What's the task I'm actually trying to do? And then we have a very, very tiny controller then that just takes that and then transforms it into an actual robot command. But the important thing is that robot command translation doesn't have to be that smart, ultimately, because the hard work has already been done by this agent. And then here's just another example, a very, very similar concept, but applied to diffusion networks, which is just another style of end-to-end control. Yeah, the idea here is that you have noisy actions, and then as part of the learning process, it just learns to denoise those actions into an actual action that came from your data set. Yeah. Okay. So hopefully I've managed to somewhat convince you of the first two, and you've learned something about where we've been in the field. But how do you get started? Well, Neuracore is one option. And where I think this is best place is, if you're really looking to kind of empower your internal operations, right? So the ultimate thing here is that we just want to give tools, right? And empower companies to be able to create these skills themselves, right? We're not here to sell a model per se. We're also not here to sell services and deliver an end solution, though that can happen. But what we really want to do is empower companies to deliver their own solutions and solve their own problems using this next-gen technology. And so, yes, I want to thank a bunch of the people I've worked with, all of the work that I talked about today. And yeah, thank you.